All right, try 5 speaks about Pythagorean triplets. We've learned prior that the Pythagorean theorem says a squared plus b squared equals c squared. Now we've, through our practice, discovered that some of these problems come out nice and neatly. Like, for example, if I have 3 squared plus 4 squared equals 5 squared, 9 plus 16 equals 25, 25 equals 25. In other words, this is a set of sides which are all whole numbers, 3, 4, 5. But it doesn't always work that way. For instance, if I were to put in values of 1 and 2, would that tell me that my largest side, my hypotenuse, must be 3? 1 squared plus 2 squared, 3 squared. 1 plus 4 equals 9. No. In this case, 5 does not equal 9. So it's not true that every ordered set, 3, 4, 5, 1, 2, 3, 4, 5, 6, that does not make a right triangle, does not apply with the Pythagorean theorem. Instead, there are very certain sets of numbers that do. 3, 4, 5 is one triplet. Those are the 3 sides of a Pythagorean triplet, always working. There are some others that we might discover using inductive reasoning, in other words, by practice. If we found 5 squared plus 12 squared equals x squared, 25 plus 144 is equal to x squared, so 169 is equal to x squared, square root both sides, and we discover another Pythagorean triplet, which is 5, 12, and 13. Now, Pythagorean triplets are great because they make it easy to work with. We know that the numbers are going to deal as nice whole numbers and not come out with crazy radical answers. Now, we will find some crazy radical answers. When we get to these later in the unit, we'll discover that 4 squared plus x squared is equal to 8 squared. 16 plus x squared is equal to 64. X squared equals 48. X is equal to 4 root 3. That's actually a really important one. It's not a Pythagorean triplet because this is not a whole number. It has a radical attached to it. It's an irrational number. So far we've discovered 2 sets of Pythagorean triplets, 3, 4, 5, 5, 12, 13. Now it turns out, you remember from our dilations, that similar triangles mean that each side has undergone a dilation, a stretch of some number, some common scale factor. So if I double each side, instead of 3, 4, 5, I make it 6, 8, 10. Turns out that will also be a Pythagorean triplet. It makes sense because it's a dilation of the other. So 36 plus 64 makes 100. 100 equals 100. This is a second example of a Pythagorean triplet. Turns out I could do any dilation of these. So I can take a 3, 4, 5 triangle and triple it, for example. 9, 12, 15. I could do any number times 3. Actually, I should write that as 3n. 4n, and 5n. I could do the same thing for my 5, 12, and 13. I can double it. I could do 10 times it. Or I can do 5 times any number, the same number times 12, and the same number times 13. There is a way in which we could calculate any other Pythagorean triplets. We could, for instance, use our formula that was derived by Plato, which is kind of cool. It suggests that if the smallest side, let's put here, the smallest side of a right triangle is n squared minus 1, the medium side will be 2n, and the hypotenuse will be n squared plus 1. You'll notice that there's a difference between the hypotenuse and another side, in this case the medium side, of just 1 in each case. Another example is 7, 24, 25. So our formula for Plato is n squared minus 1, comma 2n, and n squared plus 1. That will find for you Pythagorean triplets anytime you wish.